All right, let's tackle a big one, quantum physics. It has this reputation for being the most mind-bending, complicated subject in all of science. But does it really have to be? Let's find out.
You almost have to start with this famous line from the brilliant Richard Feynman. It's pretty intimidating, right? I mean, if one of the geniuses who helped build the theory felt that way, what chance do the rest of us have?
Well, here's the thing. That quote, it's actually a little misleading.
The truth is, we understand quantum physics incredibly well. In fact, you could argue it's the most successful scientific theory in human history. It's the foundation for almost all modern technology. We're talking the computers and smartphones in our pockets, digital cameras, those beautiful LED screens, lasers, even nuclear power. You just don't build our entire world on a theory you don't understand.
So, if you want to get a real handle on it, you need to grasp one single core idea. This is the most important concept in all of quantum mechanics. At its heart, everything is a wave. And this is where things start to get weird. You see, in our everyday classical world, we think of an electron as a teeny tiny particle, like a little ball at a single point. But in the quantum world? Nope. That very same electron is described as a spread out wave.
And this wave has a name, a very important one, the wave function. Now, don't let the name intimidate you. It's basically the quantum rulebook for an object. It's an abstract mathematical tool, sure, but it contains every piece of information you could possibly know about that object.
Okay, this next point is absolutely crucial. When we say wave, don't picture ripples in a pond. This is not a physical wave, it's a wave of probability. It doesn't tell us where a particle is, it tells us the chances of finding it in any given spot.
And this is exactly how physicists use it. You start with the wave function for a particle. Then you do a simple mathematical trick. You square its amplitude. And what you get is amazing, a probability map. The brighter, denser spots on the map are where the particle is most likely to be found if you go and look for it. We can't know for certain beforehand, but we can know the odds.
So now that we have this idea of a probability wave, let's see where it leads. Because this one concept is the direct cause of all the famously bizarre behaviors you hear about in quantum mechanics.
Which brings us to the big, central question that drove physicists crazy for years. So what is an electron really? Is it a particle, or is it a wave?
Well, the legendary double-slit experiment gives us the mind-bending answer. If you shot paintballs at two slits, you just get two stripes on the wall behind them. Simple. But when you shoot electrons, even just one at a time, you get this strange interference pattern made of many stripes. That pattern is the smoking gun for a wave. The only way it can form is if the electron's wave function goes through both slits at the exact same time, and then interferes with itself.
This bizarre ability to be in multiple places at once is called superposition. And it sounds like magic, but it's really just a natural property of waves. Think about it. If you drop two pebbles in a pond, the ripples from each one overlap and add together or superimpose, creating a new complex pattern. The electron's wave is simply in a superposition of going through slit A and slit B.
And if you thought that was weird, it gets even stranger with entanglement. See, when two particles interact, their individual wave functions can merge into one single wave function that describes both of them together. From that point on, they are fundamentally linked. It doesn't matter how far apart they are, across the room or across the galaxy. What happens to one instantly affects the other. Einstein famously hated this idea, calling it spooky action at a distance.
Okay, so this wave nature doesn't just produce weird behavior. It also sets some very strict rules for how the universe works. Let's look at two of the biggest ones, uncertainty and quantization. First up, the famous Heisenberg's uncertainty principle. It's a direct result of being a wave. So on the left, we have a perfect repeating wave. Because it has a perfectly defined wavelength, we know its momentum with 100% certainty. But look at it, it's spread out everywhere, across all of space. That means we have absolutely no idea where the particle actually is.
Now, let's flip it. On this slide, we have a sharp spike. That means we know the particle's position very, very precisely. But to build that one sharp spike, you have to add together, or superimpose, a whole bunch of waves with tons of different wavelengths. The result? You now have no clue what its momentum is. It's a fundamental trade-off baked into the universe. The more you know about one property, the less you can know about the other.
And I really want to stress this point. This isn't because our measuring tools are bad or clumsy. It's not a technological problem we can solve. This uncertainty is a fundamental, unshakable property of reality itself.
So where does the quantum in quantum physics come from? It comes from quantization, and the best analogy for this is a guitar string. Because it's tied down at both ends, it can't just vibrate any way at once. It can only vibrate in specific, fixed patterns to produce specific notes. Its vibrations are quantized. Well, it's the same thing for an electron's wave when it's confined inside an atom. It can only exist at specific, discrete energy levels or quanta.
So we've built up this unbelievably powerful and accurate picture of the universe. But for all of its success, there's a giant gaping hole right in the middle of the theory, and it's known as the measurement problem. Here's the puzzle in a nutshell. Before we look, an electron exists as this spread-out wave of all its possibilities. But the moment we measure it, the instant we look, we only ever see one single, definite outcome, a single particle in a single place. It's as if the act of measurement itself forces the wave to give up all its possibilities and collapse into just one reality.
But how does that happen, and why? What is it about the act of measuring that forces the universe to pick just one outcome from an ocean of possibilities? This is the deep mystery that Richard Feynman was really talking about.
So let's recap. The whole thing starts with one core idea. Everything is a wave of probability. From that one concept, you get wave-particle duality and superposition. It also directly leads to the strange connections of entanglement, the hard limits of uncertainty, and the step-by-step energy levels of quantization. And at the very center of it all lies the profound mystery of what happens when we simply look.
And that leaves us with one of the biggest, most profound questions in all of science. At its deepest level, is the universe truly random? Is it just rolling the dice every time a measurement is made? Or are there deeper, hidden rules that we just haven't discovered yet that are actually making the choice? The answer, for now, is still out there.